it's somebody putting pages into the service lift. Any question?
Yeah.
You'll have to shout.
The tool chain that you built, would that be the same tool chain you could use for working with the bootloaders?
Yes. Yeah, the tool chain is normally just built using a standard GNU tool chain, so yeah.
But
Same
most of
one
the
as
tool
yours.
chain has say, Linux in it. I presume there that it's binding to Linux services. So if you write the bootloader, it's not yet Linux.
Well, you won't link with a C library in that case. You will just link, well, you just compile a bunch of objects and then link them together using some special linker script. So it's not identical to doing regular stuff, but it's still the same compiler.
What's missing at that point?
Well, the main thing is missing is that there is no C library because there is no C runtime set up, because the bootloader has to start from the very first instruction. So initially you're running it in assembler code without some kind of stack, and then at some point it will create a stack, and then it will generate it will create a C runtime environment, and then you'll start writing C code. And all of that is specialized, so it's not going to be part of the standard C runtime. But don't worry, it's all worked out. You just type make, and it will do the right thing usually. Not quite. Yeah, go on.
What about barebox? Do you know this?
No, I'm not familiar with it.
Because I have a project using barebox as bootloader.
Okay, right.
And I don't know whether it's based on U-boot or Red Boot.
Oh, is that not a stripped down version of U-boot?
There is a text editor embedded, and it's quite, I think, quite flexible.
I've no experience with barebox, so I can't really comment on it. Okay, so U-boot and Red Boot are the most common you're going to come across. If you're working, of course, on PC hardware, embedded PCs of various sorts, then you're stuck with a good old PC-ROM BIOS, and you'll have to use either Grub or Lilo as a second stage. I think I'm going to call a break at this point. Can we take a 15-minute break while we try and sort this noise out? Yeah, essentially when you launch QEMU, you say how much RAM you've got, or how much RAM you want it to have. And it emulates a number of standard boards, so for the ARM processor it can emulate the ARM Versatile well, it does do, but it doesn't really expose it in an easy way. If you want to emulate your own board, you'll have to take the QEMU source and make create your own implementation. Yeah, well, I mean, it can do that, but you'd have to write the code yourself. I've never actually looked into doing that. Just give me a minute, I'm going to find out what's going on.
Excuse me, could I rearrange your plugin?
Yeah, of course. No, the thing what I'm going to do is I've got 3 presentations to go through. No, it's fine. No, it's perfect.
So I took the reply. Maybe make something about it.
Okay, right. Well, I've called a 15-minute break anyhow.
It's really because of these 2 air conditioning opening, because in the room next door they don't hear anything.
All right.
Okay. So
Well, we'll take another 10 minutes break and,
Yeah, okay.
okay, let's do that by then.
I'm sorry for that.
Maybe I'll just plug it for a moment.
Close the events bill, can we?
For the moment, I didn't use it.
Maybe we will change.
Yes.
Chris, just a quick question.
It's very fragile. Both of them, I just
Because you're just using small items, so it's not specific.
Right.
So that's the process of it.
it's when to change it. Mold it. Where do you come from?
Germany. Didn't it? Don't do it. One in Paris. Paris. But I still remember that I think it was on weekend. It was at the end. I ended in a restaurant. And then the chef.
That's exactly what I was just looking for. I'm trying to think where I've got this.
Cooking thing, and we have to make music. The whole restaurant was playing with
Dishes and
everything. I think I got the same for potato. I still remember that it was really great.
Yeah, well, I think some people have talked to the hotel management. Hopefully, they'll get this stuff along. No. Right, if anybody wants to download the slides and the notes, this is the URL. So it's downloads ELC-E 2010 Linux-quick-start RGZ. It might be worthwhile doing that. Klaus, does our Wi-Fi work?
I just unplugged the NL-UEG network because I'm going to put the main station somewhere else. But the Devere Deluxe should work.
It does seem to work, yeah.
For now. Bandwidth is a little bit slow.
So you should be able to log on to the hotel network. You just open up just make a connection to the Devere Wi-Fi, and then when you look at a page in the browser, you just need to enter your name and address, and click the button click the box that says I abide by the restrictions. quiet for the last minute. Did you speak with the hotel?
I have a long time.
Good, good. So it's time to continue with that. Yeah, I'll give it another couple of minutes just to make sure it's settled down. Right, has everybody got that? Can I take that off the screen? We will hopefully update the ELC website. If I can find somebody who knows the password, and put a link on there. Okay, is everybody here? I think there's one vacant seat over there. Do you know where the person next to you?
He should be along shortly. He's momentarily indisposed.
I understand. Well, a bit behind schedule now. So, bootloaders. Okay. This slide and the next couple are just given a few examples of what you will need to do with U-boot later on. So U-boot, in common with Red Boot and various other bootloaders, gives you a command prompt. So it's not only just a bootloader, it also is a monitor program. And the kind of things you can do with U-boot is use it to read from NAND flash a file from this offset in the flash memory, this many bytes long, and place it into RAM at this X address here. So that's how you'd load an image from NAND flash. That's doing the same from an SD card, for example, and that's doing the same from TFTP. This is what we will be doing later on. So just to point out that when we're using TFTP, of course, we'll need to set an IP address for the board and an IP address for the server we've been loading from. And then in each case, this loads an image into address 8010 and 4 zeros, here, here, and here. And then to actually boot the kernel up, you type boot M and give it that magic address. U-boot has an environment. You can see here we're calling setEnv in two cases to set an environment variable. That's just a variable in memory. You can save the environment by typing saveEnv. And typically the way this is laid out in flash memory is that we have a chunk of flash memory for U-boot itself, a chunk for the environment. So when we do saveEnv, it just dumps everything into that space there, and then whatever else is in your memory, usually one image and one or two file system images. One very useful environment variable is called boot command, boot CMD. And we'll be setting this so that when U-boot starts up, if this variable exists, it will execute all the commands stored within that variable. And in the case where you have more than one command, you can separate them with semicolons, but you need to escape the semicolon with a backslash in order that U-boot does the right thing with it. And usually you don't want it to do this straight away, so in order to give a chance to break into the auto boot sequence and type some command yourself, normally we set a variable called boot delay for the number of seconds, 3 in this case, before it starts running that sequence. If you press any key in that 3-second period, it will stop the auto boot and then you get an interactive session. I noticed out there's one of my many typos. I seem to have set elf instead of set end. So this is the Middle Earth version of the command. Right, good. Got to the end of that one then. So we have looked in some depth at tool chains. We've talked about choices of C library. We've talked about where to get tool chains from, and some of the issues about just taking the default tool chain that somebody gives you with a piece of hardware. And we've had a quick look at the bootloader and seen how that generates the hardware description of the board and passes that to Linux and loads up a Linux kernel, and so on and so forth. Okay, so those are the first 2 elements of my 4. Okay, any questions? No? Good. You must have understood that completely then. Excellent. I'm going to go straight into the next presentation because I'm a little bit behind time now. So I'll do the next presentation until coffee arrives, and then we'll take a fairly brief break for coffee, and then I'll charge on after that. Okay, so the next bit is called kernel and user space, and it's about those things. So my third element is the kernel, the Linux kernel. Let me see, I've got a bit of a digression about version numbering, a chunk about board support packages, and then how to compile one and how to boot one. Yes, this is one of my favourite slides actually. Just to differentiate, I often talk about kernel space and user space, and I just want to point out exactly what I mean by these things. The thing is that most of the time you are writing applications, and those applications will, whatever language they're written in fact, they will ultimately be bound to a C library, because the C library is the interface to the operating system, to the kernel. And all of this is user space. Now, the point is that an application can't do anything apart from make library calls, basically. It can't, in particular from our point of view, it can't access any hardware, or at least not easily. So anything you want to do, you have to make a function call. So even if you do, say, a simple printf, say you have a hello world program with printf hello world in it. That printf is a C library function. That will call a system in the operating system to actually output that string. And in the event, for example, that we're working with a serial console, as most embedded systems do, that string will have to be output via a device driver interface into the serial port. So we go into the kernel system interface, that will then dispatch it to the appropriate place, to a device driver, that will then interact with the hardware. And this slide always comes as a bit of a surprise to the people who are familiar with a more traditional RTOS model. Because if you're working in a standard RTOS, then of course there's no distinction. This is all one chunk. and hence applications can do whatever they like with whatever hardware they like whenever they fancy to. So I don't know if this applies to anybody in this room, but quite often people are porting otoscope to Linux. It means that you're going to have to take that code and abstract out the hardware dependent bits into device drivers and the rest into applications. Oh, the main difference, of course, between user space and kernel space is that when you're running in kernel space, you're running in a privileged processor mode, and hence you can access all the resources. Just ignore these people, they don't exist. Not for the moment, anyhow. Version numbering. You will be familiar, of course, that we have version numbers like 2.6 point something. The important things really are the last two bunches of digits. The 35 in my example here, that is essentially the kernel release version. And we can expect kernel releases every 10, 12 weeks, something of that sort. So Linux is a very active project. There are new versions of Linux 4 to 5 times a year, which is a bit of a challenge when you're trying to build a product. Once a kernel has been released, inevitably there are a few bugs maybe with it. So any issues that are found are fixed by a very kind gentleman called Greg Hartman, amongst others, and that produces the final digit. So 2.6.35 will be released by Linus Torvalds, and then Greg Hartman will come along and produce point releases up until the next kernel release. Usually, those bug fixes are only done until the next kernel release, and then everybody switches to the current version of the kernel. From time to time, people maintain some kernel versions for longer periods of time. So 2.6.27 has been maintained and is currently up to .54. And 2.6.32 likewise has had bug fixes and is currently at bug fix 24. So if you are planning to use your own kernel and you are interested in long-term support for, these are usually supported for 2, maybe 3 years, then maybe you would choose one of these so-called stable kernels. However, and this is the crucial bit, you have a problem. If you're working on PCs or whatever, you can just go and get your kernel from kernel.org and it'll pretty much work for you. Outside of the PC environment, particularly in the embedded environment that we're in, that's not usually the case. Some boards are well supported, BeagleBoard being one of them, for example. So you can pretty much take a mainline kernel from kernel.org, select the configuration for BeagleBoard, and it, quotes, should just work, unquotes. But that's not the usual case. Mostly you will need a board support package or BSP, well, initially from the chip vendor, and then probably from the board vendor as well. So the route is kernel.org, down to the chip vendor, that gets passed down to the kernel vendor, to the board vendor, and then that gets passed down to you. This is a real pain, because again, you are dependent on that hierarchy in order to get the support for your kernel. Usually, you will be several releases behind the main line, maybe quite a few releases behind. And again, not all vendors are particularly Linux savvy, and therefore not particularly good at producing and keeping up to date. Furthermore, if you are making your own boards, then you will have to create and maintain your own VSP. So, beware of these things. So, when I talk about board support, this is mostly the stuff that is in the kernel source code in the Arch directory. So if you look in a Linux source tree, you have Arch / things like ARM and MIPS and PowerPC, x86 and a few others. So that's where the architecture support arrives, and that's relatively static.
I'm just checking to make sure we've got a copy.
We certainly have. They'll be into it shortly. Thanks. But then there are particular implementations of, for example, ARM chips, which we call an SoC. We have things like Atmel and Freescale and TI with their various ranges of chips. So each one of them has to maintain a kernel version. Well, actually, they don't have to. Ideally, they push all their changes into the mainline kernel, but they seem not to for some reason or other. So usually you will have to go to, for example, Freescale and get a kernel from them. And then at the board level, we have the evaluation boards made by these guys themselves. So Freescale have their Babbage board and TI have their EVM board and such like. So maybe you're going to have one of those. They're quite expensive, but they're well supported. Or maybe you will use what I call a COTS, a custom off-the-shelf board, from people like Digi, Eurotech, Avantech, Mbest. There are dozens and dozens and dozens of these companies. Some of them quite small, some of them not particularly knowledgeable about Linux. So this is the hierarchy. Architecture, chip, board, you down here at the bottom. So this basically means then that, despite what I said about choosing, for example, stable versions of Linux and such like, in practice you are limited to using the kernel versions that are available for both your system on chip and your particular board. So for example, if you happen, I seem to be using Freescale chips a lot recently, if you happen to be using such a chip, you have to use the Freescale Linux kernel, which currently is 2.6.31 if I remember rightly. Or at least it was earlier this year, which is about 4 releases behind the main line. Applying the board support package. Different vendors do this slightly differently, but usually what happens is that you take a vanilla version of the kernel, 2.6.34 in my example here, and then you apply a patch, maybe several patches, with a patch tool here. And usually they will also supply some configuration information, some BSP kernel config, so you copy that to be .config at the root of your kernel source tree. And I say that's a typical procedure because that's more or less the procedure we'll be following for the LPC sticks that we have later on. And indeed we will be using a 2.6.34 kernel. When you come to configure your kernel, one of the things you'll have to decide is whether you want kernel features to be compiled into the static kernel image, the VM Linux, or whether you want them to be separate as modules. So essentially what I want to answer is the question of whether I should use modules or not. And the very quick answer is no, not unless you've got a good reason to. So here are a couple of reasons why you want to use modules. The biggest advantage is that you can load drivers on demand, which especially if you have USB or other pluggable interfaces on your board or your product, is handy because it means you can just wait until somebody plugs something in and then load the driver for it. But if, on the other hand, you don't have such a thing, then you know exactly what's going to be in the hardware every time it's turned on, so you don't need modules. Okay, well, maybe one other case. When it comes to optimizing boot time, some drivers can take significant lengths of time to probe the hardware and set themselves up. And sometimes you don't need them immediately. So you can cheat a little bit when you're trying to reduce your system boot time by loading some drivers later. And you do that by making the modules and then loading them using insmod or modprobe. But apart from that, I mostly recommend that you avoid modules and just build everything into the kernel. So you have one kernel image. It's less things to go wrong, less worry about version mismatches, etc., etc. So mostly when I'm doing my projects, I will generate just a single static kernel image which has everything built into it. And stick with that. Configuration then. A kernel, Linux kernel typically has much more than 1,000 configuration options. And getting those right can be quite tricky. And in some cases, getting just one of them wrong means that your kernel won't boot. So it's kind of crucial. So part of the board support package, as you saw a couple of slides back, is a kernel configuration, which is a default configuration for your particular chip or board, which has, hopefully, all of the features working. So typically, you will take that default configuration, and then you'll run one of these utilities here to modify it, to tweak it. Maybe cut out some cut out some functionality that you don't need to make your kernel smaller. Maybe add some more in if you're doing some debugging, for example, to increase debug support. So you run, for example, make menu config, do whatever you want, save the result, and you'll find that you have an updated file called .config in your kernel source tree. .config is just a text file containing all this stuff. And it also generates a header file, an include file, autoconf.h, which is essentially .config that in C code. So for every option in .config there'll be a hash define, which means you can then bring that into source code and do conditional compilations. And then having done that, you can at last compile your kernel. You will need to set these two variables. You'll need to set arch to be whatever architecture you're using, for example ARM, and you'll need to set cross_compile to be the prefix for your toolchain. Normally I do this by exporting them within the shell. You can, if you like, define these on the command line when you run the make. It's easier, I think, to do it this way. And then you type make either Z-image or U-image in most cases. Z-image creates a compressed kernel image, which is suitable, for example, for the Red Boot bootloader. U-image essentially takes the Z image and adds on a 64-byte header, which U-boot requires. So a U image is just a Z image plus the U-boot header. And so when you type make image, for example, it first of all will compile a file called vmlinux, which is the kernel image in ELF format, and then it will create z-image, which is a compressed binary image, and then if you type make image, it will generate a image as well. Okay, and then depending on which bootloader you're using, one of these you will use to load onto the board. You may remember that when I was talking about bootloaders, I mentioned command lines. This is a list of options which set the configuration, if you like, the runtime configuration of the kernel. This file here, this is from the Linux source code directory containing your Linux source code. Documentation /kernel-parameters.txt contains a fairly comprehensive list of all of these options, and there are many hundreds of them. However, most cases we only need to know about a dozen or so. Three examples I have here. Console. This tells the kernel where to output its messages, both when it's booting and also at runtime, in fact. And normally we'll set that to be a serial device of some kind with a baud rate. Root. This tells the kernel where to get its root file system from. So root equals /dev/ some device. And then the other two examples there, quiet and debug, they basically determine how much you get on your console here. If you put quiet, you'll get hardly any messages. If you put debug, you'll get loads. So obviously you put quiet on production systems and debug on development systems. And my fourth and final element in this part of the lecture, let's talk about user space. This is the bit, remember, that makes everything actually work, that gives us that smooth surface that makes everything look nice and shiny. So I want to look at what it is, where you get one from. I want to talk about busybox and system 5 initialization. Brief chat about UDEV, and then a few examples of mounting root file systems. So, what is user space? It is the same POSIX environment for applications, mostly POSIX. Unlike the kernel, which is neither sane nor POSIX, of course. Your user space consists of not only a bunch of programs, but also the shared libraries that they depend on, some configuration files, some device files in the dev directory, and various other bits and pieces. The first experience of user space is when the kernel mounts its root file system. So remember from the command line thing just now, we have root equals something. That essentially tells the kernel where its root file system is located, and it will then attempt to mount that file system. Typical locations, RAM disk, some kind of storage device, usually some kind of NAND flash, possibly SD card, very rarely hard disk for embedded. Or we can use the network and mount a root file system using NFS, the network file system. And in fact, we're going to start off by using NFS, and then later on we'll use NAND flash. You can probably see where I'm going here. Part of the stuff you get from your board or chip vendor will be some kind of root file system. Same kind of comments as with tool chains. Don't just take it without thinking about it. Usually it is not what you hugely want. So again, the message in my opinion, is to consider one of the community tool chains with their own root file system, such as Angstrom or Open Embedded if you want to dive in, or whatever. But don't just take what you're given without thinking about it. So, where do you get your root file system from? Probably most people actually roll their own root file system. That's kind of becoming harder and harder as embedded systems become more complex. So whereas I always used to say that's the best way to do it because it gives you the best, most tuned, most highly optimized file system that there can be, it does require a fair amount of expertise to set things up. So increasingly I recommend using either a build tool such as BuildRoot or Open Embedded, or something like Angstrom, or even things like Ubuntu ARM or Debian. The advantage of these things is that they will put together a root file system for you in a reasonably sane kind of way and make your life easier. A couple of slides on busybox. Outside of the embedded world, busybox is very little known. But within embedded, the majority, probably the vast majority of embedded systems do use busybox as a base. So just a couple of slides on what that is. You can go and get it from here. And the idea is that it gives us a set of user space programs, in fact everything you need to get a shell prompt and more. So the busybox is actually just a single binary. It includes an init program, a rather nice compact shell called Bash, which is Bash compatible but it's much smaller. Utilities for file system and network and everything else. Oh yes, and a copy of course, VI, so you can edit files. Here's a quick example of what busybox looks like. This is just a snippet, so dot there, indicated there's a lot more. But in this case here I have my copy of busybox. It's about 740 kbytes, so it's not that big. And then we have a whole bunch of symbolic links to it. So if we take the example of the cat command here, that is just a symbolic link to bin busybox. Which means that whenever I run any of these commands, and there'll be about 100 of these sim links in various places, whenever I run any of these commands, that will result in the busybox binary being loaded and called, as it says down here. And so when busybox starts up, it has to look at its first argument, argv0, which of course contains the command tail, well actually the whole command. And in my example here, argv0 will be /bin/cat, because that's what I typed. And so the The first bit of busybox is some parsing code to work out which applet it needs to go to. So it'll look at this, work out that this is the cat applet, and then jump to the bit of code that does that. The advantage of this is that because we have all this in a single executable, commands can share code between each other, whereas if they're separate commands they can't so easily do. So the whole thing is much smaller, plus the people who write busybox are very much aware of the space constraints on embedded systems, and so the whole thing is designed to be small and fast. So this is why people tend to use busybox as the basis of the user space of embedded systems. Next topic, right. Once the kernel has mounted its root file system, the next thing it will do is to run the very first program. And by default, the first program is /sbin/init. You can change this. There's a parameter called init that you can pass to the kernel to tell it to run a different program. But /sbin/init is good. And then the job of the init program is to start up everything else. In fact, init is the first program, it's process ID 1. It's actually the ancestor of all other processes. So everything that runs on your system was started ultimately from init. Common versions of init, busybox has a version, so I'll have a quick look at that. And there is the more traditional System 5 init. So I'll discuss that as well, particularly since the Angstrom toolchain we'll be using is actually System 5 based. Okay, just very quickly on this one. Busybox init, in fact both of them, will begin by reading a configuration file called init tab. So busybox init starts off by reading etc init tab. Here is a simple example of an init tab. And this block arrow here shows that actually the first thing it will do is look for the keyword sysinit, and then it will run this command. This command is etc init update rcs, and that is a shell script. And my example down there is a very simple init shell script that just mounts a couple of file systems, prompts this, and configures a couple of network interfaces. So that's pretty much the simplest form of initialization you could have. Now obviously you could fairly easily extend this to run additional programs. This point here we're actually running a getty, which means we'll get a login prompt on /dev ttys0, which will be a serial report. But hopefully you can see fairly intuitively how you would extend that to do whatever you want. System 5 init is a bit more complex. The main difference really is that System 5 init uses the idea of run levels. Okay, so you guys lost? And the idea of a run level is it defines a particular system state. In other words, what services will be running at that state. Typical allocations of run levels from 0 to 6 in this case. 0 is hold, 6 is reboot. So if you go to run level 0 or 6, you're either going to stop or reboot. Single user, meaning that essentially we only start up a subset of the services, and 2 to 5 are fully operational, undefined, but they're kind of up to you to decide exactly what they are. Usually, in fact, an example we're going to be looking at, the default run level will be 5, which is fairly common. This is an example of the init tab for System 5 init. And although it is a little bit similar to the busybox one, so this line here is almost the same. System init, etc init.d RCS. That's going to be our essentially master script. We, in addition, have this line here, which says what the default run level is. In this case, it's going to be run level 5. And then we have a set of scripts that will make us run in each one of the run levels. In fact, we just run a command called rc with the run level as its parameter. And then we have a couple of lines down here, which in this case here will, for example, launch a getty, a login prompt, and give us a login prompt on TTY-S1, in fact, which is a serial terminal. In fact, most System 5 init tabs look pretty much like this. The only thing you tend to have to change are these parameters here for the console and the baud rate, as you go from one board to another. The real work then is done with these initialization scripts, which appear in the init.d directory. This is a fairly typical example, so I'm trying to find something that makes any sense here. Yeah, for example, there's a script here called dropbear, dropbear being the SSH daemon that we'll be using. And networking, that very obviously is to do with bringing up the networking. So usually you can actually run these scripts from the command line by giving the script name and then either start or stop. Some of them take the parameter restart and maybe some others too. But, oh, I haven't got the slide. The way it's meant to work is that we create symbolic links to these scripts that are per run level. So we will have things like in etc rc5.d, for example, we'll have a bunch of symbolic links, something like s, 10 syslog. That's not a good example actually, but they usually begin with an S, capital S, and then 2 digits, and then the name of the service we want to start, and that will be a symbolic link to the syslog script in etc.d. We may also have some symbolic links beginning with a K. I can't think of a good example, but K05 something. That would kill off a service called something. So the idea is that as you enter a run level, as you leave a run level, you kill off all the kill scripts in the current run level, and you start all the start scripts in the next run level. So as you switch from one run level to another, you kill some services and start some other services. And that's essentially the secret of run levels. And I say all of that because we'll be looking at this again in the practical session shortly. Right, next topic. Device nodes, things that go in the dev directory. Remember these, most hardware appears as device nodes in /dev. So you can't really do that much until these things are created. The old-fashioned way of doing this is to create device nodes by hand with the mknod command. But this is maybe a little bit tedious, a little bit error-prone. So increasingly we use dynamic device managers, such as UDEV, to create these device nodes for us. And so you'll find many embedded systems are using UDEV these days. I'm a little bit uncertain as to whether it's a good idea or not, honestly. The benefit of using UDEV, and I should warn you, well, I should say that Open Embedded and Angstrom do use UDEV by default. The benefit is that you don't have to worry about creating these device nodes, they're all created for you, which is nice. And also it will handle essentially hot plug, it will create new device nodes on the fly as necessary. Guys, there's a space here. Oh, there's a couple over there. So UDEV is in one sense a good thing, but its major problem really is that it is quite slow. So if you have a system where you are worried about boot time, it's sometimes a good idea to get rid of UDEV. It can take several seconds to populate the dev directory. Okay, I think the final topic I want to look at is where this root file system is going to be located. And I'm first of all looking at using NFS to mount a root file system over a network. And indeed, this is what we normally do during the development phase of an embedded system. The advantage being that if the root file system is on, for example, my laptop or a PC, we have very little restriction on the amount of space we use, the amount of storage. We've got gigabytes of storage to play with. It also means that I can update files in that directory tree on my laptop very quickly and easily, and the target board will see them straight away. So we're going to start off doing it this way. Very briefly, to make this happen, you will need to export a directory by putting a line such as this into etc exports on your laptop, well, on your development system. And then when you boot your kernel, you'll need to add to the command line something along these lines. So here we have root equals dev NFS, RW because we want it to be readable, writable. NFS root equals the address of the server, my laptop in this case, and then the exported directory on that server. So that bit there is the same as that bit there. And then because we need a network, we're using a network protocol, we need a network address. So we have to pre-configure that with ID equals and a suitable number. So this is what we do in most cases starting a project. However, sooner or later you're going to have to put it into some permanent storage. Most often flash memory. So this gives me a chance to have a quick look at NTD and various flash file systems. this is a stack that Linux uses to access flash memory. Starting down at the bottom, we have the actual chips themselves, usually NAND flash chips of some kind. Above that, we have the Memory Technologies Device layer, MTD, and that has chip drivers that can access various chips of various sorts. The MTD layer then gives us raw access to the flash memory, and then on top of that we will use a flash-aware file system such as JFFS2, YAFS2 or UBFS. And to tell Linux that we want it to mount a root file system in this way, we will have on our command line something like root equals /dev/mtd block and then some number. mtd block because we will be using, well, certainly in these two cases here, we'll be using a block device on top of mtd. The number 1 in this case is the partition number. And then especially in the case of JFFS2, you have to tell the kernel what sort of root file system it is with FS type. With most other file system types, actually the kernel can probe the device and work out what it is. But it turns out that one of the peculiarities of JFFS2 is that you can't do that. So you have to tell it at the type of JFFS2. So here's a very quick overview of flash file systems. JFFS2 has been around for a long time, and it's the most commonly used one. But it has some downsides. It's not particularly fast, it's its biggest problem, especially at mount time. So it can take tens of seconds to mount a JFFS2 partition. YAFS2 is another fairly common option. It was developed after JFFS2, so it's optimized really for NAND flash chips. And it's interesting to note, for example, that most Android phones use the YAFS file type for their storage. But it's not part of the mainline kernel. If you want to use YAFS, you'll have to go and get the patches from, I think they're at yafs.org now. Can't remember, Google it. And then the newest one is UBFS, which has been around for a few years, but not as long as the other two. UBFS actually is a file system that sits on top of a block driver called the unsorted block image block driver. So it's actually two components. There's UB and then UBFS on top of that. Doesn't really matter. The net result is that it is both robust and fast. So I would tend to use UBFS in any new projects. And I would tend not to use JFFS2 if I can help it. Okay, good. Come to the end of that. So let's now look then at the final two elements of the four. We've looked at the kernel. We've talked in particular about VSPs and the limitations that causes. We've also looked at compiling and booting kernels. And we've looked at user space, what it is, where you get it from, a little bit about initialization, and some stuff about root file systems, and using either NFS to mount during development time, or using typically MTD and a flash file system to mount during production. Okay, and that is the end of that section. Right, any questions?
You were saying it'd be better to not use modules at kernel boot time.
Yep.
You often get into problems of GPL though, in fact that your rendered modules are not GPL.
So modules aren't GPL?
Well, they're developed them themselves, obviously. They don't want to give away that source code. If it were part of the kernel in the product, you'd have to give it away, wouldn't you?
Yeah, but I think you'll find the modules are covered by GPL as well, in most cases. The only case that a module is not covered by the general public license is if it is not a derivative work of the kernel, which basically means either it predates Linux or it was developed for a different operating system and ported to Linux. And even then, that's frankly a little bit dubious. So it's a mistake to think that modules avoid the GPL,
Right, okay.
unless you've got a very good lawyer, of course. But it's best to assume that all kernel code is public, it is GPL.
Indeed,
Sorry,
yeah.
is open source, I mean.
Yeah.
Regarding the UTF-S file systems and especially the GFFS2 and UBFS, I presume both of them are compressed in memory, in flash memory space.
Both GFFS2 and UBFS do have compression as an option, yes.
Yes, and what is the compression level of both? Are they comparable, or one of them is better for example, I don't know, for a system that is limited in flash memory space?
They are roughly the same. I think they both have an option of either using zlib or LZO. They both have essentially the same compression options. UBFS is less efficient in space usage because it takes up about 5% of the flash storage for its own directory structures. And it also has a journal which is some megabytes, I don't remember how big it is exactly. So UBFS is not suitable for systems with small amounts of flash memory, say less than 32 megabytes. But 32 megabytes plus, I would say the overhead probably isn't that much. Okay? Okay, right. Well, the coffee and the biscuits arrived actually some time ago. So let's go and demolish those. How are we doing time-wise? We're kind of okay, actually. So we'll take a 10-minute break, and then we'll resume, hopefully refreshed and reinvigorated. A bit of a rush around here, I'm afraid, so I'll just take it one at a time.
No, just for the moment. Just 91%. It's okay. Do you attend the second workshop? Enjoy it?
Possibly not me, but I just want to slip it around through 45 degrees. Yeah, thank you. Take a break. Yeah, I'm happy to do that. exactly. Well, I say just, I am a freelancer.
Well,
I say
a
contractor.
contractor.
Yes, exactly. Yeah. So.
You're just based here in the UK? Or?
Yeah. I live in Winchester, which is way down south.
Way down south. Okay. That doesn't really matter. So, okay. And you just work for other companies doing the systems? Or?
Yeah. Yeah. So I do a lot of training. There's a company called FIVAS who I do a lot of training work with. So essentially I just subcontract with them and they send me to exotic locations to train people.
So you go throughout Europe or?
Yeah, and the US, yeah.
Oh, okay. Okay.
And occasionally the Far East.
Okay, so you actually train or you actually do specific medical work for school?
Well, I do both. So I spend about half my time training. Well, actually, a quarter of my time training these days, and the remainder doing this regular freelance work.
Right.
Kind of optimizations, bug fixing, writing device drivers,
Right.
U-boot and Red Boot customizations, all
Right.
that kind of stuff.
So do you go actually to premises to do training, or do you have?
In terms of training, mostly we do what we call on-site training, which are actually on the customer's premises.
Right.
But the company I train with,
Yep.
they do public courses 6 times a year.
Right.
So that's basically booking a hotel and anybody who wants to come along.
And how long are these courses usually for?
5 days.
So they're pretty intensive, all day, 5 days?
Yes.
Yeah.
Yeah, so I do one, for example, that is about embedded Linux, which is more or less what we're covering here, but you can.
In a bit more detail, yeah.
Another one on device drivers, please. Yeah. Training. About 2,000 engineers through those by now.
Over a period of time?
Yeah, about 8 years.
8 years, oh wow. That's a lot. And what is, do companies normally send a whole team of people, or just one or two? And then go back and train their own people? I mean, it's usually a team.
I don't know, it depends. I mean, the bigger companies tend to train whole departments, so we've done a lot of training, for example, with Intel, and also with Hewlett Packard. And basically, so you know, sometimes you'll find that you'll constantly go to the same place for weeks and weeks, and until you've gone through the whole department, and then you don't hear from them again.
Right, right. I'm based in Canada. We're looking at opening an office in Europe, and I'm just trying to get a feel for what the expertise that the community is like. So, I'm just wondering, you know, where all where's the hot bit of talent? Is it kind of like a triangle somewhere? I think it's a lot of independent stuff going on.
I don't know. I'm not sure I can really
Because
answer
I
that.
visited Free Electronics, they're a little bit better.
Yeah.
So, you know, I'm just trying to get a kind of a list of expertise going on, so that because relocating people here is a little bit different. So, stuff. Yes.
So